Hey folks, I'm Mr. Hartzler and I want to talk to you today about nth roots, radicals, and rational exponents. So let's get started by looking at our target. So here, I can relate roots and rational exponents and use them to simplify expressions and solve equations and other kinds of problems. So the vocabulary here, our index. Well, it's important to know what the index is. Our index is whatever is outside of the radical. So here is our radical symbol, right? Down there, looks just like that. But the number that's out here, for a square root, we don't write anything there. It's just assumed to be a 2. But for all other roots, I have to write it in there. So a third root would have an index of 3. A fifth root would have an index of 5. And then a 13th root, though we don't really get there often, would be an index of 13. Now our nth root, that's just referring to this little equation here. So if I had something like x raised to an nth power equals c. So nth root, that just means whatever that exponent happens to be. That's the root I would need to find out what x is. Then again, a radical symbol is just that little, that squiggly line. You've done that a bunch of times. And then the radicand, that's the thing that's underneath here. That's the thing that's underneath my radical symbol. That's my radicand. All right, let's go and look at some examples. Here I want to find real fourth roots of 81. So that means I need to find the fourth root, or fourth root of 81. Well, that means I need to start trying to break this up, do one of those little factor trees. I do actually kind of a lot in class. So let's see, fourth root of 9 times the fourth root of 9. Break that up even further. The fourth root of 3 and the fourth root of 3. And then this 9 breaks up, right? Fourth root of 3, fourth root of 3. Whew! Now, when I'm breaking things up, usually it's just a square root, so I only need 2 things. Or really, I just leave it like square root of 4. Well, that's just going to get me a 2, right? But that's because of something. That's because the square root of 4 is the square root of 2 times the square root of 2. And since my index, that little number there, it's assumed to be a 2 for square roots. Since that is a 2, I only need 2 of the exact same thing to make a normal of that same thing. So here, since it's a fourth root, I need 4 of them to give me a normal 3. And we have to keep in mind that when it's an even number of things, that could also be the negative version. So that means that I could have fourth root of negative 3 times negative 3 times negative 3 times, 4 of them's a lot, times negative 3. So if I had 4 of those, that's still the fourth root of 81 because all the negatives cancel out. So that means my answer is positive or negative 3. But because they just asked for the real ones, it's not both of them. It is just the positive version of it. Okay? Cool. Now, let's go over and look at what are the 4 roots of 16. Now, this doesn't say anything about real. This just says what are the 4 roots. That means I need to split this all up into all of its little roots. So a 4 and a 4, 2 and a 2, and then a 2 and a 2. And again, it says the 4 roots of 16. So what are the 4 things it breaks down into? These here. So my answer is 2, but again, it could be negatives of all of those things, so it's also a negative 2. Okay, again, even-powered roots. I'll even write that. Even-powered roots have positives and negative solutions. Odd roots only have 1 solution. So we'll get to examples of that, but it is important to note there's only 1 if it's an odd root. It couldn't be positive and negative. It has to be positive or negative. But again, you'll see that in some of our next examples. So here, a little bit different than the thing we just talked about. I'm just converting rational exponents to radicals. And then actually in the second half, we do the other way. So this, where do roots grow? Like tree roots? Well, they grow underground. So roots go on bottom, and power is something that goes on top. So I'm going to put power on top, roots on bottom. So here, I'm actually going to start off by writing that 16. So here's my 16, and I know I'm going to need a radical because I'm either I'm converting rational exponents, rational meaning like ratio or fraction. So I'm converting that fractional exponent into a radical. So if I start off with an exponent like that, I'm going to have to add a radical. All right, so my power is on top. My power goes with that number. Then I have my root. my root is the 4, and it goes out here, right? Like 4th root of 16 to the 1st. And we can actually simplify that all the way down. Technically, I just need this, but what 4 things multiply to give me a 16? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the 4th is going to get me 16. So another way I could write this. So again, right here, that's the conversion into radical. But just to keep going with this a little bit further, that can be written as the 4th root of 2 to the 4th, right? Because it's 2 to the 4th power that gets me 16 still. And then those 4s are going to cancel, and I'm left with just a normal old-fashioned 2. Okay, just so we kind of have that idea in there as well. So now this next one, I need to convert that again from rational exponent into radical form. So my big number comes down. My power is a 4. It goes with my 7. My root is the 3, and it goes out here. So this, this one, I'm just going to leave it as is. I don't want to do 49 times 49, which is, or like 4 times 7, which is 49, times 7, times 7 again. That's obnoxious. And I have to find the cubed root of it. Ugh, not right now. So we're going to leave it like this. Just do the conversion. And now over here, I have to go the other way. So I have 2. It's my main number. It's my base. And then what is the power on that 2? Well, if it's not written there, it's assumed to be a 1. So that's a 1. My root is a 6. So power over root, 2 to the 1/6. Then we've got, wow, a lot of stuff over here, right? We've got a couple of things. So first off, I am going to take this 5. What is the exponent on it here? Well, a 1. What's its root? A 4. And all of that is being raised to the 5th, which we're not quite there yet, but these two things are going to get multiplied, right? Do a little bit of foreshadowing here. So this is still 5 to the 5/4 is what this is going to be. Okay. Power over my root. It still applies here. Let's go and look at our next example. What is the meaning of the exponent? And then we're going to simplify these ones too. These are a little bit nicer than the other ones. So 25 to the 1/2 power. Well, that's, again, power over root. So that means I'm taking the 2nd root of 25 to the 1st, or just 25, right? It's all the same there. And a 2 out there is just a square root. We just usually don't write it because it's assumed. There's no first root, right? I mean, the one thing that multiplies to get that is just that thing. So here, what 2 things multiply to give me 25? Well, split that up. 2 of 2nd root of 5 and a 2nd root of 5. I just need 2 of them, because that's my index, to get me one normal thing. So both of those together are going to get me a normal, not a 2, a normal 5. Nice. Also, you can kind of think about that, just square root of 25. Done. Here, we're getting a little bit more interesting. 32. What's my root? What's the thing on the bottom half of that fraction, my denominator there? So 5th root of 32 squared. Now the nice thing is, this is where PEMDAS can be a little bit flexible. So I could square the 32, or I can take the 5th root of 32 and then square it, similar to what we did on that last one. What is the 5th root of 32? Or what 5 things multiply together to get me 32? Well, a 2 times a 2 gets me 4. Times 2 is 8. Times 2 is 16. Times 2 is, 32. Sweet. So that is 5. Oh, sorry. 5. Yeah, I'm going to write this. Of 2 to the 5th, because there's 5. I counted them there with tally marks. 5 2's inside of that 32. And then it still has to be squared. Didn't mess with that. But 32 is the same as 2 to the 5th power. Hopefully we agree with that. But now the 5th root is going to cancel with that 5th power there. So I have a 2 inside my parentheses now. Still needs squared though, so that's a 4. So again, I have my power on top and my root on bottom. I get to choose which one of those I do first. Usually, not always, but usually the root is easier. Let's make this number smaller, then let's make it bigger. So let's look at this next one. 121 to the 3/2 power. So that's the power on top, root on bottom. Okay, so that means square root of 121 to the 3rd. Whew, sounds muddy, right? But I can mix that up because, again, just to show you this, that 3/2, that's 3 times 1/2, or 1/2 times 3. That's the commutative property of multiplication. I can mix and match, or not mix and match, but I can switch the order there. So instead of doing the cubed part first, I'm just going to do the 1/2 part first, which is a square root. So I'm going to take the square root first, then I'm going to cube it. So what is the square root of 121? 11. That's that denominator of 2 parts. So I've done that. I'm going to cross that out. But now I have to cube it. Oof, this does get a little bit muddy. 11 cubed. Be right back. I'll do that math. All right, so that is 1331. Awesome. Let's keep going. All right, we're looking a little bit more sketchy, right? But I've told you, that number outside my index, that tells me how many of the exact same thing I need in order to be able to pull it out, make it normal. So I'm going to simplify some stuff in here. This 32, that's the same as 2 to the 5th power. 32 is kind of a common one us teachers use a lot because, you know, it can be a high exponent, and so we can still get that. And then m to the 15th. Well, that's m cubed 5 times, or then to the 5th power. That ends up being the same thing. We're going to do this a couple of ways, but I want to show you this one. So 2 to the 5th, and then the 5th root of it. I'm going to then bring out just the one normal 2, because that 5 will cancel with the 5 out front. And this 5 will cancel with the 5 out front and just give me m cubed. Okay, that's my answer. But let's look at this another way. I'm going to split this thing up a little bit. The 5th root of 32 and the 5th root of m to the 15th. I need to try and split this thing up. 1, 2, 3, 4, 5. 5th root of 2. 5th root of 2. 5th root of 2. Oof, there's so many of these things. There they all are. So since I have 1, 2, 3, 4, 5 of them, that's all I need because that's what my index is. Means I can get out one normal one of them. I get a normal 2. My m to the 15th, similar setup. So I have m cubed, m cubed. All right, so I have 1, 2, 3, 4, 5 of these same things multiplied together to get me m to the 15th. Right, so I multiply these, I'd add their exponents up. Just like x times x gets me x squared, I add those exponents. So that means one of them comes out like normal. And I get an m cubed. Let's look at this next example. Cubed root, so I need 3 of the same things again. And the 8 part, there's a cubed root of -2, cubed root of -2, cubed root of -2. 3 -2's get me a -8. So that means I only need my index, I only need 3 of them. Normal 2 comes out. Now, how many a's are there underneath this radical? There are 3. Perfect. That's the number it takes in order to pull one of them out. So I get 1 normal a comes out of that. Then c's. Well, I need groups of 3, and there's going to be 2 groups of 3's. So that's c squared. And then for d, yeah, you can kind of get the pattern, right? There's 3 groups of 3's in that, so that's going to be d cubed. Hopefully you kind of notice a trend. We don't officially know it until like section 2 or 3, but this number out in our power, we could divide it by that, right, and get these numbers. That's kind of like if we were to move this into the exponential form, right? Or sorry, the rational exponent form, right? I'm going to leave the 2 as is. I think we are good with that part. But let's look at the a cubed, and it's the cubed root of that, right? Let's put that into rational exponent form. So that's a to the power over the root. Well, 3 over 3 is just 1, so that's just a. Cool. But then it's c to the 6th, and the cubed root of it. So that's c to the power over the root. Oh, well, that's c squared. And then we have d to the power of 9, the root of 3. That gets me d cubed. Those letters, just like these. Kind of neat, I think. Let's do this next one like that. So I now have an index of 4. I'm going to take all of these and take them to that 1/4 power, right? Or the 4 as my denominator power. So q power 12 over the root of 4. And then a z power of 4 root of 4. And now I need to simplify those fractions. 12/4 gets me 3. And z, 4 over 4 gets me a 1. I don't need to write that one either. That's kind of nice. So q to the 3rd z. Cool. Let's go on and look at our next example. All right, here, a little bit more work, right? I need to divide both sides first by whatever number is in front of that number, that x, my variable. So divide by 5, divide by 5. I know, kids, I don't give you a calculator, but 300 plus 20, right? That's the same thing as 320. Divide all that by 5. So 300 divided by 5 and 20 divided by 5. 300 divided by 5, well, 300 or 30 and 5 is 6. So 60 plus 4, so 64. Cool. X cubed equals 64. And here, I'm actually going to use something slightly different than taking the cubed root. I'm going to take it to the 1/3 power. So that's the same thing, right? If I'm taking the cubed root of something, the power of 1, I'd assume, then that's the same thing as a to the power of 1 root of 3, which is kind of neat. It's kind of fun. So x equals, because these two things are going to cancel then, 64 to the 1/3 power. So what 3 things multiply together to give me 64? That's 4. And because this is an odd index, I cannot use -4. Because a -4 times a -4 times a -4 is going to get me a -64, and that's not what I was taking the cubed root of. So that does not work. It has to be a +4. That's what I was saying earlier. If I'm using an odd index, it must be that number and nothing else. It can't be the positive or negative version of it. It has to be either positive or negative. It can't be both. Now let's look at this one. 9x cubed divided by 1125. Let's divide by 9. All right, so now I have divided by 9, and I get 125 equals x cubed. Yeah, I know, I cheated. I used the calculator. It's cool. Now I need to take the cubed root of this, So what 3 things are going to multiply together to get me that 125? Don't know off the top of my head, so let's break it up. Cubed root of 25 times, there's 5 quarters and 125 cents. Then I need to split this one up further. Cubed root of 5 times the cubed root of 5. Well, I have 1, 2, 3 of them. That's my index. That's how many I need. And that gets me 1 normal 5. Cool. And that equals x. Now, could it also be -5? No, it cannot. It has to be +5. And let's go on and look at our next example. All right, so before I start this, I actually want to show you one more thing, because I haven't done this example yet. What if I had the cubed root of a -8? Well, this splits up into 3 things, right? Cubed root of -2 times the cubed root of -2 times the cubed root of -2. Now, I know it looks kind of sketchy, but I'm allowed to take the cubed root of a negative number. Because, again, these numbers multiplied together are okay. Odd roots, it's allowed to be negative. Because this is a -8, it's fine. What 3 things multiply to get me a -8? Well, these 3 -2s. And that doesn't work for positives, because then they end up canceling out, and that looks kind of sketchy. Anytime stuff cancels out, you should be a little concerned. But here, it doesn't cancel. We end up with that negative. It's fine. So the cubed root of a -8 is actually just a -2. That's it. Not positive. It has to be that -2. One cube has an edge length 3 centimeters shorter than the edge length of a second cube. The volume of the smaller cube is 216 cubic centimeters. What's the volume of the larger cube? All right. So I'm going to write down that, let's see, S is going to be small side, so the side of the shorter cube, equals 3 centimeters shorter than the other one. Oh, I'm just going to let this one equal S. So small side is just going to be the small side. But then the large cube, its side length is going to be S plus 3, right? Because it's 3, the small one's 3 inches shorter. So I have to add 3 to the small side in order to get my long side. Now I'm going to compare volumes. The volume of the smaller cube is this. So volume of small cube equals 216 cubic centimeters. And what's the volume of the larger cube? So what's the volume of my larger cube? Well, I know how to find the volume, right? That's S plus 3 cubed. Okay, that's not bad, right? But I don't know what S is, and it doesn't look good. I don't want to FOIL that. That seems obnoxious. So I'm going to come over here and see what I can do. Volume. That's just the side length cubed if it's an actual cube, right? So my S cubed equals 216 centimeters cubed. What's that going to be? 6 maybe? Because it ends in a 6. So 3, no, not 3. 6 times 6 is 36. Let's multiply it by one more 6. So that gets me a 6 and a 3, 18, 19, 20, 21. That's it. Cool. So it's, if I take the cubed root of both of these things, My S must then be 6 centimeters. So now I plug that 6 in. Volume of my larger one equals 6 plus 3 cubed, which equals 9 cubed, which equals, I don't know, I'm going to cheat and look at the calculator for that. 729. And don't forget your unit, centimeters cubed. Not too bad, right? And look at that, we're done with this video. Awesome. Make sure you do math carefully and with enthusiasm. And of course, folks, don't do drugs. Have a great day, everybody.